right, let's start. Joel. Hello, hello, hello. How are we doing today? Raise the roof. All right, good. All right, we're going to get started. Any last bathroom breaks? When those happen unexpectedly, it's not good. I can speak from experience. Okay. Hey, got in front of him. A lot of moments in that episode, eh? All right, friends. So today, machine learning. Okay, we'll talk a little bit about our homework, which finally is about to drop. Thanks for your patience. And you're like, oh, where's my homework? I want my homework so badly. Yes, thank you. Yeah, homework. Jack, you're gonna get murdered after this. You realize? Yeah. So yeah, let's walk you through. So we'll talk about the homework, and we're gonna talk a little bit about these optimization algorithms that you've all been using, but really haven't been like in Keras, things like the atom optimizer. We talked about it in somewhat hand-wavy fashion. We talked about gradient descent, but I want to talk about other different ways to optimize these weights in your networks, okay? Because there are lots of approaches. But anyway, so for today, let's go here. Okay, today, 2026, 0310. All right, so your homework 2. Number 2, okay? So this is all going to be about neural networks, deep neural networks, okay? Okay? All right. So it's going to be a few things. So one, everyone is going to be using Keras to regress a function, okay? And we have our examples in Keras from classes you can follow along, okay? That's going to give you a bunch of weights, okay, and biases, okay? You use Keras as your interface for TensorFlow, okay? Got some drop frame issues, but we'll get over it, okay? All right, so weights and biases for TensorFlow. That's going to give you some weights and biases, okay? But this is what I feel like it's a rite of passage for anyone doing neural nets as part of their machine learning curricula, okay? For everyone, you're going to want to do forward propagation of your network using NumPy, okay? Not using Keras. We did a little bit of this by hand. We did sort of like a single node neural network version of by hand, but I've given you all the equations to do it for a multiple neurons, okay? All right? We're going to do forward propagation. That's everyone, okay? But for the grad students, you have the ultimate rite of passage, okay? Which you're going to do back propagation. Using NumPy. All right? Okay? So basically, you're going to be regressing, using use stochastic gradient descent, SGD. You find the weights. Okay? All right? Okay. It's going to be due the Friday after spring break, okay? All right? So you have, I don't assume people do homework over spring break. I'm not a monster. Okay? Yeah, you're welcome. So it's sort of like 2 weeks without spring, not including spring break. So it's going to be due. I like applause. I'm on television. For guys shaking out the applause, it's fine. Why do I think I'm in this business? Anyway, I'm just kidding. All right. Due 5 p.m. Friday after spring break. Next week is spring break. Okay. All right. Enjoy. We all need the break, even the faculty members need a break. So, okay. So those are the 3 key components that you're going to do. So you're going to do a little bit of Keras on your own, And again, these are going to be submissions just like before. You're going to send us links to your Google code, right? Okay, pretty easy submission. All right, I will say, this is for grad only. This is grad only. You know, if you're undergrad, by all means, give it a shot. Okay. Question. The audio's crackling. Yeah. So let's do a little slightly different. Could be my corduroy coat. And crackle sound. Tell you what. Let's try this real quick. Testing 1, 2. Testing 1, 2. You should see a second to know if that actually worked, right? Okay. Sorry, friends. Let me just mute this for a second while I Okay, I'm back. Let's try that again. Let me know. Pops up. Okay. In the worst case, I'll use my Mac mic, which is not great, but okay. All right. Let me know if it pops back up. Give me a signal. All right. Okay. So we've got this. So this is for graduate only. It's only required for graduate students. All right. It's going to be more intensive, but it's an important thing to go through. Oh, that sucks. So what we're going to do. Okay, let me know if that comes through. Okay. I'm using every device in my possession to give me an audio. Okay. I'm gonna be like those YouTubers. They hold a microphone like this. Okay, that's what they love to do. Oh, let's see. I have to do okay here. All right, testing 1, 2. Testing 1, 2. We'll see how this goes. It's good to give an audio afterwards. So hopefully that's at least understandable and it's crackling. Oh, really? Let's try one more thing. Try one more thing. It could be the connection. Okay. So I want to get sure this is all good. Let's do the MacBook microphone. Testing again. All right. So we'll keep pressing on. We're recording on there as well, right? So we have that. That makes good. Okay. All right. We've got back propagation. All right. So 5 p.m. Friday after spring break. All right. Any news? Testing 1, 2. All right. So let's keep moving on. So today, it's not the microphone. It's the connection through through the thing. Okay. Here's what I'll do. Oh, you know what? That's good. You know, as a TV person, we know that's what's super important. Okay. Let's go back to this. We will upload the better version of the audio, which will be locally captured here. Okay. Hopefully this works well. Thanks for your patience, folks. It's a bit of a technical wizardry we're doing. I know all your professors have 2 backup mics for your lectures, right? It's very true. Okay. Testing again. All right. Let's go with that. Local recording. So today we are going to talk about optimization methods. Now, which algorithm have we been most talking about in this class in terms of optimization methods? Gradient descent. We've mostly used gradient descent. Gradient descent. Also, the version where you only use a couple of samples of the gradient, they're taken at random, What's that called? Stochastic gradient descent. Stochastic means random. Or SGD. Okay? All right. And when we're using Keras, and we're deciding what optimizers to use, they have a lot of fancier optimizers. We use something called Atom. Okay? Which is an adaptive moment version of stochastic gradient descent. It's very fancy, okay? But these are not the only ways to optimize anything, okay? Your neural net, your weights in your neural network or otherwise. And also, how do some of these things work? I want to give you a little bit more background on that today, okay? So, for instance, let's talk about a couple methods. So, something called Newton's method. I'm going to ask who's heard of Newton's method, but they're probably going to be thinking about 1,000 different things because Newton invented everything. Invented calculus. Yes, what's Newton's method? That's correct. That's correct. The idea is that you have a guess as to what your solution is, and then you look at the tangent line to your curve, and you see where that tangent line intersects 0, and that's your next guess. It is not an optimization method per se directly. It's a solving method, okay? So it's a Newton's method. It's a method for finding zeros, okay? There are lots of methods of finding zeros, but Newton's method is very simple. Let's say you have some function, f of x. There's f of x at x. All right? Give a little more space here. And that's our function. We want to know, where does it cross 0? Okay? And Newton's method is an iterative method, just like gradient descent, where you start with a guess. You got to start with some kind of guess. Let's say here, it's a weird function I chose. All right? Here's my initial guess. We'll call it x0. Okay? Then what you do is you take that guess and you draw a tangent line. You find out what the derivative is at that point. You draw a tangent line, and you find out where that tangent line intersects 0. Okay? Call that x1. Then what do? You find out where the function is at that point, the value of the function at that point. You find the tangent line. Okay? And you find out where it intersects 0. That's x2. Okay? And if your function is well behaved, isn't too jumpy, it'll get closer and closer to finding the root. Think of it a root finding. You know, we know that roots mean finding zeros. And you're like, that's nice, Christian. Newton does a lot of things. Sometimes people call this Newton-Raphson. That's for finding zeros. What does that have to do with optimization? Anyone want to take a guess? Yes, in the back. Finding where the gradient is 0? Is that important? What does that have to do with optimization? You're right, to be clear. What does that have to do with optimization? It's the local minima, or at least an extremum. Yeah. So if you find where the gradient is 0, that's a local minima, right? So imagine, instead of trying to perform Newton-Raphson to find the minimum of a function, use it to find the minimum of a gradient of a function. Okay? So you can use Newton's method to find where a gradient intersects 0, and therefore a local extremum. Okay? And that could be a local minimum, for instance, okay? All right. So that requires computing the gradient of a gradient. We had a word for that. We talked about it before. Anyone remember what it is? It's like a second derivative. That's close, close. It's the Hessian. Hessian. You're close. Hessian, right? So it requires calculating the second derivative the Hessian. Okay? So you have some function f. That's your function. Then you have your upside down delta. That's where your gradient. And your delta squared, called your Hessian. Okay? So if you have an optimization problem where you know what the Hessian is, that's good. Imagine you had a function that was actually written out as a bunch of algebraic terms. Okay? You can take two derivatives of that, no big deal. Congratulations, you got your Hessian. Now, to be clear, remember our Hessian, okay, is a matrix. The gradient is a vector. Okay? You're going to have a bunch of terms in a matrix for your Hessian, right? Okay? Computing the Hessian is great if you can exactly compute derivatives. I mean, and I'm talking exact. I mean, like cosine is the derivative of sine for whatever function you've got. That kind of exact, right? But if you are trying to do things like finite differencing to compute what your gradient is, you bump a thing a little to the side to see what happens to the gradient. And you have to do it again for the Hessian. That gets tricky, okay? There are methods of computing a Hessian. There's something called BFGS. Okay, this is a big whirlwind tour of different optimization methods. All right? Okay. Requires calculating the second derivative, the Hessian, all right? So if you have your Hessian, Newton's method might be really good. Okay? However, computing the Hessian can be a bit of a pain. All right? So it's one of the reasons that we often rely upon gradient descent. We don't have to take a second derivative. Okay? All right. But the idea of Newton's method, so let's go back to Newton's method. For root finding. Okay. So step one, guess a value of x where a 0 might be. Just guess a value of x where a 0 might be. Okay? Okay? Number two, evaluate f of x and the gradient of f of x Now step 3, we have to update x to be the intercept of the tangent line with the x-axis. Okay? All right? Then number 4, you go to step 2. Right? All right? That's the high level, okay? When we get a chance to actually have some code, my coding setup's not working great here today. We'll have to do it from our Thursday coding lecture area to be able to code this up today. So we'll go over more of the equations for it then, how we update it. But the nice thing is that this works not just for one variable input x. It works for many, okay? Again, if you have a Hessian, right? Oh, sorry, I should say that's Newton's method. If you would then use it for optimization, you needed a Hessian, okay? All right. But often we don't directly use the Hessian for gradient for there are lots of ways where you don't have to use the Hessian for optimizing. Gradient descent is one of them, okay? But there are methods of improving gradient descent by sort of pretending that you know what the Hessian is, okay? So, for instance, if you have an example, okay, you've got some function f of x with x here, okay, right, and that's your function, right, and this is your initial guess, x0, right, and if you did gradient descent, you would probably end up right here, okay? Okay. Would sure be nice if we ended up over here, but you can see how that could happen, right? This is a better solution if this is your if you're trying to optimize, right? Okay? So to augment gradient descent, so gradient descent can easily get caught in local minima. By design, it's supposed to slow down when you get down to the bottom of a trough, right? But people have found out really interesting ways to improve gradient descent. So let's look at gradient descent. So one such method to avoid certain local minima and accelerate convergence is called momentum. And we know, we're mechanical engineers, we all know the technical meaning of momentum, right? So when you're moving, you want to keep moving, right? Here we mean it more metaphorically, that the gradient is moving quick. Maybe you should still keep moving quick. Maybe instead of as soon as your gradient updates, you don't just forget the last gradient. No, you're on a roll. Keep moving faster, okay? So the idea is you can modify your gradient based upon past gradients. And there's a really simple way to do this, okay, with momentum, all right? So the idea is we know, so with gradient descent, we start with some x0, and that's our guess, okay? And we say that the next guess, we often talk about in terms of w's, but I'm using x's today, sue me. All right, let's see. That your next guess, xk plus 1, is equal to your previous guess minus some step size, I call it alpha, people call it different, some step size or learning rate, times your gradient of f of x, Gesundheit. Okay? Or that is your gradient. We'll call it g. And xk is going to be gk. Right? That's gradient. Oh, that's sorry, not the alpha is not part of that, to be clear. Right? We've done gradient descent many a time. You did it for your homework. Homework 1. Okay? So you can view this as xk plus 1 is equal to xk minus alpha gk, where that's your gradient. Okay? What if we modified this gradient? Let's modify the gradient to include the history of prior gradients. Okay? How can we do that? Well, let's create a modified gradient. We'll call it BK, called the modified gradient. This is something that's updated from step to step. It's our modified gradient with momentum, where we take some previous value of BK and we'll call it BK. We'll call BK plus 1, apologize, is equal to mu, some constant, times BK plus your gradient K. Sorry, I'm going to do a slight goof here. It should be a K and a K minus 1. I apologize. All right. Okay. You're going to update your modified gradient. Okay. Now, what's happening here? This is what we call a momentum constant. Okay. Okay. If mu is 0, then your modified gradient is not modified at all. This term goes away. Right? So your modified gradient would just be your gradient if mu is equal to 0. Okay? That's no momentum. Okay? But the larger you make it, more momentum. I shouldn't say mu 0. So if mu is greater than 0, that's momentum. What's happening? Okay? That means if you had some previous gradient, that's going to be stored in bk minus 1, okay? And it's going to be sort of averaged in a way with your current gradient, okay? It's going to cruise it along. Okay? And as a result, your xk plus 1 is equal to xk minus alpha, not times your gradient, but your modified gradient, bk. Okay? So you update in step using a modified gradient. Okay? And situations where you had that little double hump that we had before, okay? all of a sudden, it can jump over those little humps sometimes and get to the bottom, okay? And you can see, look, this is not rocket science math. It's a little modification to the algorithm, okay? All right? And so this idea of having momentum is critical for methods like Atom that work better for these neural networks, okay? It's a little more complicated than that, but this gives you a flavor of what's happening behind the scenes, okay? The Atom stands for the adapted moment. It's an adaptive moment. It's not just momentum, it's adaptive, all right? But you could potentially sort of squint and see, it's sort of a squint and see sort of idea that this curvature, you know, which is all second derivative stuff, okay? If you're taking big step, and then like it's decreasing steps, that can be captured a bit in the memory of previous steps. That's sort of encoded in this one variable, bk, that's being modified by previous gradients, okay? It can make it accelerate your problem faster and skip over local minima. But naturally, if you make this too big, it can go crazy. Too much momentum. You have to stop at some point. Okay? That makes some sense? Just modifying the gradient. Okay? All right. Let's talk about some other ideas within optimization, because all of the optimization we have been doing has been saying, hey, find some value that hits some local minima, right? That's great. Nothing else to worry about. Just get to the bottom of that curve wherever you can. Preferably the global minima, but probably the local. Nothing else to consider. However, in real life, we have all kinds of things we want to consider, okay? Such as constraints, okay? For those of you in my applied optimal control class, you're seeing constraints all the time. Here, very few, okay? So unconstrained optimization, I'm going to put in quotes, is easier than constrained optimization. As a general rule, that tends to be the case. Okay, you have limits on what you're allowed to explore. So an example for neural networks could be, I don't want my weights to go below 0. Why do you want to do that? That might depend upon certain kinds of problems. But if you want to do that, you have to add constraints or some way to prevent it from going through past some value. Okay. There are also, in theory, it would be nice if you could tell an optimization that something that it comes up with must be true. It would be nice. Like, what if you said for your neural networks, like, yeah, I want you to minimize this cost. I want you to fit this curve, you know, as well as you can. But you exactly have to fit this one point right. Okay? Or you have limits on your, if you have any kind of limits, right? So constraints are conditions on what must be true of a solved optimization. Optimization, comma. While the cost function is just a suggestion. Okay? Oh, it's good. I did not know. I'm glad I did so much to fix it. Great, thank you. Running a TV production here. We're going on. All right, so, okay, just a suggestion, right? The cost function is going to try to minimize. But if it doesn't minimize it, the optimization doesn't necessarily fail, right? Whereas if I told it, you have to make this true, and it doesn't, that's bad, right? So how can you include constraints? The thing is, unconstrained optimization is easy. We just do gradient descent. We do atom. We do momentum-based methods. It's awesome, right? Constrained optimizations are harder. So how do you do it? There are methods. So one is you can treat constraints as a penalty on the cost. Okay? We haven't talked too much about reinforcement learning methods yet. That's its own section of this class. But that's a classic example where you are just having your model try things. And then you see how it works, and then you reinforce it with good when it's good and bad when it's bad, right? We do this all the time with walking robots. You know what's really bad what the walking robot does? Falls down. Yes, thank you. Exactly. I also have experience with that. Okay. So it's real bad. So what you could do is you could say, yeah, I want my cost to be low. And if I fall down, I'm adding a huge penalty to my cost. That's bad. So the optimization, which is trying to lower cost, is going to try to avoid falling, right? Yes, question.
That sort of
Yeah.
Pricing it, like, oh, have sense.
The question is the penalty something that you put in designing the algorithm? The answer is yes. Okay. This choice of the, going back to how we define a machine learning algorithm. What are the 4 key components? You need data. You need a model. You need a cost function. And you need an optimization algorithm. We're focusing on number 4 today, right? Okay? The choice of cost function, who chooses that? We do. So we have to tell it what's good and what's bad. Oh, so you're talking about, okay, how it's actually detecting if it falls, okay? Yeah. Often with a robot, we don't do it on the real robot because falling is bad on a real robot. Pro tip from Dr. Hubicki with the shirt. Robots falling down is bad in real life. Breaks the robot, okay? Shirt's proof that I know what I'm talking about. What we do is do it in simulation. We'll test it in simulation, and we'll say, oh, if the robot body is this low, we said it fell. Bad. Give it a huge cost, huge penalty, right? Then try again, right? That's how we detect it in the simulation, okay? Yeah, if you're doing reinforcement learning in real life with real life things, you have to be careful not to break whatever it is you're reinforcing. Great question. Thank you. Awesome. Any other questions? All right. So one is we can treat the constraints as a penalty on the cost. So imagine we have let's say we have a limit on some decision variable W, okay? Well, we could add a penalty, we'll call it P of W, where let's say we want it to be less than, we say that W has to be greater than some value. We could say here, above some value, good, penalty is 0, right? Above this, whoosh, big penalty, right? That could be some kind of exponential, e to the W, right? Or e to the minus W, depending upon the direction. Question? No. I'm stretching my arms as well. Oh, gosh. Oh, I had physical therapy yesterday. This hurts. Okay. Had me do so many push-ups. All right. All right. So, oh, my pecs, they hurt. Okay. All right. So we got limit on W, right? You can add a penalty like that, right? So if it goes in this area, that's bad. And your gradient descent's going to be like, that's not good. Go back in this direction. Okay? So you would add the penalty to your cost. Okay? You can be creative about this. Back in my misspent youth, this is what I did, okay? Well, as my master's, you can actually find my master's thesis online. I was just a, wee rascal with cost penalties. I was trying to do cost functions. I was literally trying to do a computer simulation of a robot trying not to fall down. It was a simple little stick figure robot walking around. And I'm just like adding penalties like crazy. Like, okay, if it gets too low, add this exponential, then add this other exponential, this other thing. I was just literally like kind of crafting this thing, this cost function, to get the robot to do what I wanted it to do, which eventually did. But those penalty functions were ugly as heck. I didn't like looking at them. Okay, all right. No, look, no shade on my former self. I learned other methods, right? Okay, so you can get creative on penalties. That's totally cool. All right. Okay. Number two, there's a much easier way to handle certain types of constraints. Okay. If there are constraints on your decisions, on your parameters for your models, the things that are directly in your decision vector, right? If it's limits on those, if you go outside those limits, bring them back. That easy. Okay. So if you run your gradient descent and for some reason it says this value w, forgot to label my axes, I'm a bad boy. Okay, all right, there we go. All right, if it goes outside of that limit, just bring it back to the limit. That's easy. Okay. You can project decision variables outside of the admissible range back to the edge of the admissible range. Admissible set. Okay. You have a limit on W. You're not supposed to go over there. If you end up there, just bring it back to there. Between iterations. That's not too hard, right? But that only works if your constraint is on an actual variable, actual decision. So on actual decision variables, not some function of decision variables. Linear functions of decision variables, you can do it. That's doable. But nonlinear functions of decision variables, more generally, that's harder. Okay, you can't really do it the same way. It's trickier. Okay. Right. That's how you can handle constraints on decision variables. Okay. Number three, if you have general constraints that you want to satisfy, we use something called a Lagrangian. Okay, this is general constrained optimization stuff. It's beautiful. Okay, it can be trickier to solve, but it's beautiful, these techniques. Okay, so the idea is that when you have an unconstrained problem, there are no constraints on it, you're just looking for the minimum, right? That's all you're looking for. So this is an unconstrained problem. There's f of x. Excuse me. Here's x. There's the minimum, right? Now I'm going to put a constraint on the same problem. And now, so you have f of x. And I'm going to say that x must be greater than, yeah, that's number one. X must be greater than or equal to 1. And that's right there. That's not allowed. The minimum that wasn't there before, that was there before, is no longer allowed. Okay? The minimum subject to these constraints is right there, right? Okay? And a way that you could view this, I'm going to make this a different color, make it red just for my notes, okay? Okay? you could view this as being some kind of force that pushes out the optimal solution from where it was, make that green, okay, to where it is. Sorry, to where it is. Some kind of constraint force. Okay? That pushes it out. All right? And that constraint force is what we call a Lagrange multiplier, or lambda. Okay? All right? The idea is that you have, so what you want to minimize is this, what we call the Lagrangian L, where you have some cost function, f of x, that's your cost, which doesn't start with g, cost, plus some lambda transpose g of x, where these are equality constraints, meaning you want to minimize f of x, that's your cost function. Hope we've got that in our brains right now. You want to minimize cost, right? Subject to the constraints that g of x is equal to 0. This is going to be more familiar to my applied optimal folks, but that's all you need to know. All right? That's called an equality constraint. It's some function or set of functions that when you plug in your value of x, has to equal 0. All right? There are two types of constraints, equality and inequality. All right? Saying that I have to, I think I can throw. Saying that I want to throw this and have it hit exactly that spot right there, exactly what I wanted. That's an equality constraint. Thank you. Thank you. Right. No. I'm adding the please, no applause. All right. That's an equality constraint. I wanted to hit that exact spot. Right? But saying I want to go at least past that spot, what type of constraint is that? Inequality constraint. Thank you again. Right? Equality and inequality constraints. You can see the way we've written this. We've written this as equality constraints. Mathematically, how we set up this problem, equality constraints are easier to deal with, okay? That if we minimize So what we are looking to do is we're looking to minimize and find the arguments that minimize, as we call that argmin in the past, right? We want to find the x's and the lambdas, okay, that minimize our Lagrangian, f of x plus lambda transpose gx of t, right? And that will give us our best decisions, right? Okay. And that will be the case at when not only, and of course this is all together. What's that called all together right there? Lagrangian. You didn't make me rhyme. Great. Lagrangian, right? L. Okay? So when we're trying to find the minimum of this problem, we're not only looking for partial L partial x is equal to 0 as our first order necessary conditions, the bottom of the curve. Excuse me. We also need partial L, partial lambda being equal to 0. We're not only searching for the decisions x, or w as we call it in the class, that minimize it. There's also these Lagrange multiplier. Those are the forces that are pushing your solution away from their optimal value to the new optimal value with constraints. Okay? You're all mechanical engineers, right? Anyone heard of Lagrangian mechanics? I probably, because I babbled at you about it a few times if you're in my other class, right? Okay? This is going to look mighty familiar, but not with these sort of metaphorical constraint forces where you're pushing solutions in places. We're talking physical constraint forces. I have this object in my hand. I'm keeping it from accelerating. I'm grabbing it. Or I have a pendulum and I'm swinging it. That's a physical pinned constraint to the world. Do you know what we call those constraint forces in Lagrangian mechanics? Lagrange multipliers. Okay? It's a direct physical analogy to the physical world. Okay? This optimization world. Okay? So you could do gradient descent on your Lagrangian if you have equality constraints, where you're trying to find your decision variables and the Lagrange multipliers. There's going to be one Lagrange multiplier per constraint. Lambda per constraint. And lambda is a vector of Lagrange multipliers. Okay? That's pretty neat, right? I know this is the whirlwind tour. This is the survival guide to the constrained minimization. Okay? But I'm sure you're like, well, Dr. Hubicki, what about the inequality constraints? How do you get that to work? Well, let me show you a cool trick. All right, again, we're going to be blasting through this. If you want to learn more about this, it's actually in chapter 4 of the Goodfellow text. They talk about this. Okay? What about inequality constraints? Okay, how do we handle those? Well, if we can find a way to turn inequality constraints into equality constraints, we know what to do, right? We do the Lagrangian. We minimize the Lagrangian. We just set this up. Okay? Well, my friends, what if I had a separate set of constraints? I'm going to call them G ineq of x. I'm going to leave a conspicuous space here, not by accident, okay? Is equal to 0. And then I add a new variable called s squared. Here's an equality constraint that is mathematically the same as saying, interesting, if s is any value, any real number, then this is going to be positive, right? Then that means that G in EQ, in order for this to be true, must be less than or equal to 0. Right? We're squaring this. This can't be a negative number. We're not going to do imaginary numbers. Get out of here. Okay? That must mean that G in EQ of x must be less than or equal to 0. We turned an inequality constraint into an equality constraint. But it requires this additional variable. We no longer just have x's and lambdas. we now have new variables for our optimization problem. These are called slack variables. Note that s squared must be positive. We're only dealing with real numbers here. Neat little trick, right? Inequality constraint's now an equality constraint. But as a result, we now have we not only have to worry about whether or not partial L partial x is equal to 0, and that partial L partial lambda equals 0, also partial L partial s for your slack variables are equal to 0. So you add more constraints. Okay, so if you have inequality constraints, you say, hey, I'll go back to it in a second. They get added to this little g of x, right? But they are of this form, where you add a slack variable s squared must be equal to 0. Okay? And these conditions have a name called the KKT conditions. They are the Karush-Coons-Tucker. I think I spelled that right. I forgot to write this in my notes. Conditions. And if memory serves, Coons-Tucker were like these very established theoreticians in this field, and they established like, oh, isn't this a cool technique? This is great. Then they found some student who published it some years earlier called Karush, who figured it out beforehand but didn't get all the credit. So they just called it the Karush-Coons-Tucker condition. Nice story. KKT, right? Conditions. But you can see these are just extensions of the first order necessary conditions, that your derivatives must be equal to 0. Okay? That thing you learned in Calculus 1, the derivatives equal to 0, it carries very far. Okay? Question? Just s squared, so it's not a single value. So it's a decision variable like anything else. So if x is a decision variable, that can be anything as long as it minimizes the function. Yeah. Sure. Yeah. 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 This puts it as an equality constraint of the form g of something is equal to 0, right? And so part of that function is this variable called s, right? So if you are going to take the derivative of, try to find where this is minimized, okay? All of a sudden, I'm probably not answering your question right. I have to go back and forth on it, Jack. Okay, so that's going to be involved in this function. I feel like there's 3 steps ahead of me. I'm missing something. Yes. You are absolutely, yes. You are yes. So in this, if you're doing gradient descent, you'd be perturbing lambda. And so now, with KKT conditions, argmin x lambda s, let's write it out more explicitly, okay? Where it's f of x plus, let's just call this lambda EQ transpose, call it GEQ for equality constraint of x, okay? Plus lambda NEQ transpose G NEQ of x plus s squared. Does that track? Where, of course, lambda is going to have both lambda EQ and lambda NEQ. Okay? Yeah. Now, if you could actually do this analytically, you can write out the gradients yourself for your problem and things like that. You come up with these cool conditions where you actually have something called, where you have a term that looks like this, where it'll be lambda times s is equal to 0, where one of these things has to be 0. This is not on any quiz or anything. This is just fun. for me. Okay. Lambda times, okay, S is equal to 0, meaning that in order to solve the problem, one of these two things has to be 0. Okay. So when you go into the constrained optimization literature, they'll call this complementarity condition. And what do I mean by that? It's not a complement with an I where you're saying nice things. This complement with an E means these have to complement each other. One has to be 0 or the other one has to be 0. At least one of them's got to be 0. Okay? Like they work together. Not that they just say nice things. But both are good parts of team building. Okay? All right? So that's just that's a rapid fire background in constrained minimization. That's part of the optimization section of the class of the textbook, the Goodfellow text on deep learning. So if you're saying, look, all we're doing is all this unconstrained minimization, how do I do something else? This is how you do it. How do you add constraints? If you're in my other class on applied optimal control, we use solvers that under the hood, inside of their code, they're computing the KKT conditions. They're stepping around with these slack variables and these lambdas and things like that. Try to minimize it subject to the constraints. Okay? That way you can hit it exactly where you want it to go. Perfect. Anyone heard of the Texas sharpshooter? Okay, what is Texas sharpshooter? Anybody? I saw nods. Now everyone's shy. It's a fallacy in logic where you basically the idea is that if you take a shotgun, shoot it at a barn, and you draw a target around the hole, like I bet they hit there. Texas sharpshooter. So and that follows to all kinds of interesting logical analysis of claims. And if you're like, oh, this thing happened, therefore it must have always been that way. It's like, no, it's just lucky that thing happened. You said after the fact, that's what you meant to do. Anyway, none of that's on the exam or any exams because we don't have exams. So, all right. So, constraints in a nutshell, right? And we still have 15 minutes left. 13. How about that? So you're getting, my friends, derivative-free optimization. So much of what we're dealing with is all these gradient-based optimizations. And believe me, when you have a good gradient, it's awesome, right? But you can still get trapped in local minima. You can mess with those momentum-based requirements and try to get out of those local minima. But sometimes you just want to try something different, okay? One thing that's really cool, I love, they're called evolutionary and genetic algorithms. Okay? And the idea is you don't have just one initial guess, my friends. Nay, 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 nay. You have many initial guesses. You could almost think of them as a population of initial guesses. So let's see, okay. So let's say we have a bunch of initial guesses. And you randomly generate them, okay? We'll just make them like, oh, look at all these initial guesses. Let's try all these initial guesses. I'm just drawing them as circles like they're little creatures, okay? Oh, look at those adorable little creatures. Look at a little smiley face on them. Happy little creatures. Happy little initial guesses, right? Each one of those has all your values of W, your decision, every single decision variables in them, right? And you say, yay, they're happy, they're happy. Okay? Then along comes a monster. Okay? Okay. All right? And it's going to eat the worst of these, the ones that have the lowest, highest cost. It's not so cute anymore, is it? Okay? Cruel. Cruel program. But it doesn't need all of them, does it? Here are the best ones. They survived. What do? They live free, have little babies. Okay? They repopulate. Okay? Now, but they repopulate in a way where their children are slightly different. Yes, question. Lowest cost, I'll say. The lowest cost. Thank you for bringing my metaphor to reality. I appreciate that, Christian. Okay? Lowest cost. Right? They repopulate, but they are slightly different. They are slightly mutated, if you will. Maybe all of those variables in your decision variables, maybe you add a little random number to them. Okay? They are slightly varied. Okay? Then, roar! So sad. So sad. But some live on. What do? They have babies. They repopulate. Okay? So you select and repopulate with variation repeatedly. Okay? This is called an evolutionary algorithm. You can see the analogy, right? The fittest are surviving and reproducing. And guess what? At no point did we compute a derivative. We just take a population we randomly generated. We check we check the cost. The higher cost values, go. How many survive? That's up to you. How cruel are you? All right? Okay? But you can see a trade-off. If you say only one survives, then you're not going to get much speciation and diversity in your little simulated population, right? They're all going to converge to very similar results. But if you allow several to survive, maybe you get different options that can each live in this nice diverse little wilderness inside your computer. Okay? Getting better and better solutions. Okay? And they are devilishly fun. Oh, not devilish. That's the wrong phrase for this. They're so much fun to program. Okay? And it's not that hard, right? You're not doing backprop. Okay? But imagine, these little populations here. These like this little guy right here. That could be all the weights in a neural network. This could be all the weights in a neural network, right? So if you ever see the phrase neuroevolution, that's what we're talking about. We're talking about evolutionary algorithms applied to weights. Okay? Okay? So the decisions that you make, you come up with your cost function. You come up with the ways you repopulate and your selection criterion for what survives. And what we call the mutation operator. Right? It could just be like, oh, here are all your numbers, right? This is 1, 4, 5, and 3. After the mutation, it might be, oh, it's 1.03, 3.98, this is 5.17, this is 3.2, right? This could be just a random mutation. Add a number to it, right? Mutation operator. That's what makes it an evolutionary algorithm. It's the selection and variation. All right? Now, I also mentioned something called a genetic algorithm. It is extremely, extremely similar, okay? The only key difference is that genetic algorithms have a crossover. Mutation. Crossover. What's that mean? That's like reproduction. That's not like with two individuals. You actually take the genomes of two individuals. We'll call that here, P1, P2. Let's just say that there is here and here. You have two parents, okay? And the crossover mutation might go where you now have half of the numbers from one and half of the numbers from the other. Right? So it kind of gets a mix from multiple parents. You can pair them up however you want. It's up to you. You can be creative with this. A little too creative, but that's what an evolutionary genetic algorithms are. This could be a list of whatever kind of numbers, including the weights in a neural network. Isn't that neat? Look at all the ways you can optimize. We have 4 minutes to spare. I'm going to be nice and let you out early. Any questions? All right, thank you so much. I'll see you on Thursday for remote. Seconds.